All right, so now let's look at the science test 2. The passage says modern science exclusive of geometry is comparatively recent creation and can be said to have originated with Galileo and Newton. Okay, let me just put on the pen over here. Okay, just okay, so it says that the modern science has been originated with Galileo and Newton. Galileo was the first scientist to recognize clearly that only one way to further our understanding of the physical world was to resort to experiment. So he says that Galileo was the first one to resort to experimenting. Yes. However, obvious Galileo's contention may appear in the light of present knowledge. It remains the fact that Greeks, in spite of their proficiency in geometry, never seem to have realized the importance to experiment. So, can we say that Galileo experimented and Greeks did not experiment? Okay, to a certain extent, this may be attributed to the crudeness of their instruments of measurement. Still, an excuse of this sort can scarcely be put forward when the elementary nature of Galileo's experiments and observations is recalled. That means Galileo's experiments and observations. So Galileo's experiments and observations had not much to do with measurements. Okay, they did not have much to do with measurements. Watching a lamp oscillate in the Cathedral of Pisa, dropping bodies from the Leaning Tower of Pisa, rolling balls down the inclined planes, noticing magnifying effect in the spherical glass vase, such as was the nature of Galileo's experiments and observations. So very simple things. As can be seen, they might just as well be performed by the Greeks. So even the Greeks could have done this. At any rate, it was thanks to such experiments that Galileo discovered that the fundamental law of dynamics, according to which acceleration imparted to a body is proportional to the force acting upon it. So this is how he realized that F is directly proportional to A. The next advance was due to Newton, the greatest scientist of all time, if account of his joint contribution to mathematics and physics. As physicist, he was, of course, an ardent adherent of the empirical method. Ardent is very passionate, adherent, someone who always adheres to it, someone who always follows it. Okay, of the empirical method, observational method. But his greatest title to fame lies in another direction. Prior to Newton, mathematics, chiefly in the form of geometry, had been studied as a fine art without any view to its physical applications. So before Newton, geometry was only studied as subject and no physical applications were sought out. But with Newton, all the resources of mathematics were turned to advantage in solution of physical problems. Thenceforth, mathematics appeared as an instrument of discovery, the most powerful one known to man. Just one moment. Okay. So, but with Newton, all the resources of mathematics were turned to advantage in the solution of physical problems. Thenceforth, mathematics appeared as an instrument of discovery, the most powerful one known to man, multiplying the power of thought, just as the mechanical domain, the liver multiplied our physical action. So just this whole thing is an example. Is the pen not working? Right, so this part. Why is the pen not working? Okay. Yeah, now it's working. All right. So where were we? Yes. So this guy applied maths, okay, and that actually was used like a lever. So very hard problems of physics were very easily solved. Okay. So it's the application of maths to the solutions of physical problems. This combination of two separate fields of investigation, which constitutes the essential characteristics of Newtonian method. Okay, so basically the Newtonian method was combining physics with maths. Thus, problems of physics were metamorphosed into the problems of mathematics. That means they converted the problems of physics into the problems of mathematics. But in Newton's day, the mathematical instrument was still in the very backward state of development. In this field again, Newton showed the mark of genius by inventing integral calculus. So now this creativity that Newton showed was inventing integral calculus. As a result of this remarkable discovery, problems which would have baffled Archimedes, problems which would have confused Archimedes, were solved with ease. We know that in Newton's hands, this new departure in scientific method led to discovery of law of gravitation. But here again, the real significance of Newton's achievement lay not so much in the exact quantitative formation of the law of attraction, as in his having established the presence of the law and order, at least in one important realm of nature, namely in the motions of heavenly bodies. So it's not that he actually got the formula correct, or it's not that actually he got the value correct, but it's that he could apply them to those natural bodies, heavenly bodies, is what is great over here. Nature thus exhibited rationality and was not merely blind chaos and uncertainty. To be sure, Newton's investigations had been concerned with but a small group of natural phenomena, but it appeared unlikely that this mathematical law and order should turn out to be restricted to certain phenomena. And the feeling was general that all the physical processes of nature would prove to be unfolding themselves according to rigorous mathematical laws. That means nature obeys math. Okay, in very short, if we have to summarize all of this third paragraph, it's that nature obeys math. When Einstein in 1905 published his celebrated paper on electrodynamics of moving bodies, he remarked that difficulties which surrounded the equations of electrodynamics, together with the negative experiments of Michelson and others, would be obviated if we extended the validity of Newtonian principle of the relativity of Galilean motion. So basically, Einstein's talking about what Newton and Galileo did, and how this would change, or how the implications of their work would change if we use this person's work, if we use Einstein's work, which applies solely to mechanical phenomena so as to include all manner of phenomena, electrodynamics, optical, etc. So basically, Einstein is saying that mechanical phenomena is very well defined by Newton and Galileo, but what his work is, it defines electrodynamics, optical, etc. also. When extended is the way of the Newtonian principle of relativity became the Einstein special principle of relativity. Its significance lay in assertion that absolute Galilean motion or absolute velocity must ever escape all experimental detection. That means you cannot detect absolute velocity. Henceforth, absolute velocity should be conceived as a physical, meaningless, not only in the particular realm of mechanics as in Newton's day, but in the entire realm of physical phenomena. So basically here he's coming down and saying that absolute velocity should be considered physically meaningless. Okay. Einstein's special principle, by adding increased emphasis to the relativity of velocity, making absolute velocity metaphysically meaningless, created a still more profound distinction between velocity and accelerated or rotational motion. This later type of motion remained absolute as and real as before. So which motion remained absolute? Accelerated or rotational motion remained absolute, okay, as before. It's more important to understand that at this point and to realize that Einstein's special principle is merely an extension and the validity of the classic Newtonian principle to all cases of phenomena. So here he says Einstein added to what Newton says. Okay, all right, so that is how we can understand this passage. Let's go forward and look at the question. The first question reads, according to the author, why did the Greeks not conduct experiments to understand the physical world? Okay, now if we look at Greeks, I think the Greeks part came over here. Right, however obvious Galileo's contention may appear in the light of our present knowledge, it remains fact that Greeks, in spite of their proficiency in geometry, never seem to have realized the importance. That means They did not think it was important enough. So apparently they did not think it was necessary should be our answer. They focused exclusively on geometry? No. Their instruments of measurements were very crude? No. Greeks considered the application of geometry? No, not really. So A should be our answer. Okay, all right.